All right, now we're going to look at some examples of dealing with equilibrium problems when we also have a pH issue to take into account. So the first one is example 8.4. It says, what's the aluminum ion concentration in a saturated AlOH3 solution? And they give us the KSP. It's very, very small. Right? So we do this like we do any equilibrium problem. We write our equation. We say AlOH3 solubilizes, or if it does, not very much, we get Al plus 3 and 3 OH minus. Now, they don't give us a pH. So if they don't give us a pH number, we assume it's 7. And the reason we do that is because that's the neutral pH solution. But the reason we have to take it into account is because OH minus is one of the ions. And so that's a reason to include it. So now we can write our equilibrium expression. We would say KSP 1.9 times 10 to the minus 33rd is equal to X, the amount of aluminum ion, times 3X, the amount of OH minus ion, plus what's already present due to the pH being 7. Might be a different number in a different problem, and we'll get to that in a minute, and all that raised to the third power. So now we need to see if we can make this simple by making an assumption. We want to see if 3x is irrelevant compared to 0.05 times 10 to the minus 7th. That way, from sig fig's perspective, we could ignore it. So I divide both sides of that equation by 3. I get x is 1.67, or has to be less than 1.67 times 10 to the minus 9th. If I do that, then I can line out my 3x, because really it's so small, I'm only concerned about the 1.0 times 10 to the minus 7th cubed. So our equation reduces to this. So it's pretty straightforward to solve for x. Divide both sides of this by 1 times 10 to the minus 21st, which would be 10 to the minus 7th cubed, gives us a value of x 1.9 times 10 to the minus 12th. Now, that's a good assumption. It's a good problem. But what if we had not taken pH into account? Well, if we had not taken pH into account, then we would ignore the 1.0 times 10 to the minus 7th, and I end up with x times 3x quantity cubed. So that becomes 27x to the 4th. Divide both sides by 27, take the 4th root of that number, and I get 2.9 times 10 to the minus 9th, which is off by a factor of about 1,000. So this is why we need to take into account all the factors that we've got going on. All right, let's take a look at the next one. The next one's 8.5. How many moles of chromium hydroxide, chromium 2 hydroxide, can be dissolved in 1 liter if the pH is 8? KSP for this material is 6.7 times 10 to the minus 31. Now we know pH, we're going to have to take it into account because OH minus is going to be a factor in this solubility problem. Because the pH is 8, that means that OH minus concentration is 1 times 10 to the minus 6. Remember, POH would be 14 minus pH, and so that would be 6. So OH minus would be 10 to the minus 6th. We've got our equilibrium reaction, our equilibrium equation. So we set this up just like the last problem. We say KSP is 6.7 times 10 to the minus 31st, and that's equal to X, the amount of chromium, times 2X plus 1.0 times 10 to the minus 6th quantity squared. So we do this exactly the same way. We say, hey, if we can make this assumption, that would be that 2x would be less than 0.05 times 10 to the minus 6. So we could get rid of it by significant figures. So x is now less than 2.5 times 10 to the minus 8th, and that reduces our equation to this, okay? Because we can get rid of the 2x plus term. So we just solve for x, and we get x is 6.7 times 10 to the minus 19th. Now, that's pretty small, pretty insoluble. And so what we've said is that's 1.5 moles in a billion liters. Very, very small. All right, now we're going to talk about the method of successive approximations. And this is a technique that we can use when assumptions don't work, but I don't have a quadratic, because we can solve a quadratic. It's what do we do when we have some higher order equation. So we look at example 8.7. So how many moles of FeOH3 can be dissolved in 1 liter if the pH is 5.3, KSP is 1.1 times 10 to the minus 36? We write our equation just like we always do. And if pH is 5.3, that means that OH minus, well, POH then would be 14 minus 5.3, which is 8.7. So OH minus is 2.0 times 10 to the minus 9th. We take the anti-logarithm of that number. We get that. We write our equation same as before. But here we're going to have to make a simplifying assumption, because if we don't, we're going to have a 3x cubed, which would be 27x cubed, times x, or an x to the 4th term. So let's see if we can make this simplifying assumption. We do this the same way we've done all the others. 3x less than 0.05 times 10 to the minus 9th, divide by 3. X is 1.7 times 10 to the minus 11th. And this reduces our equation to this. But the problem is when we try to solve that, I get x is 1.4 times 10 to the minus 10th, and my assumption is not that good. Okay, I'm off. But this really puts us in a jam, right? Because either we have an invalid assumption, which we don't like, or we have a 4th order equation, which we also don't like. But we can do a new technique, okay? So this is an iterative procedure, which means we do it over and over again and see if we can converge on an answer. So first thing we're going to do is we're going to assume that x is 1.4 times 10 to the minus 10th, even when we know it isn't. Now, we're going to plug this into the red part here, the 3x plus 2 times 10 to the minus 9th, and I'm going to solve for the remaining value of x, which is in front of that cubic, okay? If I do that, eventually the value of x converges on an answer. Converges is just a nice math term, which means it stops changing. So when we do it the first time, of course, we get 1.4 times 10 to the minus 10th. We plug that in and we do it again. We solve for x outside the parentheses the second time. We'll get a number that's 7.8 times 10 to the minus 11th. Okay, so we take that number, we plug it into the 3x plus 2 times 10 to the minus 9th cubed, solve for x. I get 9.9 times 10 to the minus 11th. So I think if you look at the top number, you see that's really 14 times 10 to the minus 11th. So we started at 14, went down to 7.8, do it a third time, it comes up to 9.9. I plug that number in, I solve for x a fourth time, and I get 9.1. I do it a fifth time, 9.4. I do it a sixth time, 9.3. You can see that the answer is starting to, each time I do it, the change gets smaller and smaller. I do it a seventh time, again, 9.3 times 10 to the minus 11th. So I now have my answer. In reality, it's not a whole lot different than my initial assumption, which was 14 times 10 to the minus 11th, but it gives us an accurate answer. Okay? So it took 7 iterations to do this. Not particularly easy, but after the first or second time, you kind of get into a rhythm and you see how to operate your calculator quickly, efficiently. You know how to solve for this. Depending on the number of sig figs you have, might be 6 iterations, might be 12 iterations to converge. So you just keep doing it. All right, let's take a look at a couple more questions. Number 1, which pair will dissolve to form a buffer solution? Remember, to form a buffer solution, you have to have a weak acid and its conjugate base, or you have to have a weak base and its conjugate acid. Conjugate means it has the same anion or cation root. So when we look at HCl, they both have chloride, but HCl is not a weak acid, so A is not correct. I look at B, they both have sulfate, but H2SO4, again, one of our strong acids, not a weak acid, so B is not correct. C, I have a weak acid and a salt of a weak acid. That looks like that could be legit, but let's check out the other two possibilities. On D, I have a weak acid, all right, but rubidium fluoride is not a conjugate of nitrous acid, so D isn't right. And on E, I have a strong acid and the salt of a strong acid, so E cannot be right, so our answer is C. All right, number 2, I have a 1 liter buffer solution containing a 1.00 molar ammonia and 1.00 ammonium chloride. What's the pH? Well, for this, we can use our Henderson-Hasselbalch equation. All right, now, we know the Ka, in our case Kb, and we can take the negative logarithm of it to get pKb. Now the question is, what's A minus and HA? But if you look closely, you see that they're both 1 molar. So 1 over 1 is 1, and the logarithm of 1 is 0. And so now pH is just equal to pKa. So if I take the negative logarithm of 1.77 times 10 to the minus 5th, well, I've taken that's the Kb, not the Ka. So I need to take that number, add it to 14, and I get my final answer of 9.25. This will probably be the last one we'll have time to do. Number 3, an additional 150 grams of solid ammonium chloride is fully dissolved into the solution in problem 2. What's the pH? Okay, we've got to find the molar mass of ammonium chloride, which would be NH4Cl, and that's 53 grams per mole. So 150 divided by 53, that's 2.83 molar. So now we use a Henderson-Hasselbalch equation, and we say pH is pKa, or pKb in this case, which we know. And now I say plus the logarithm of A minus over HA. Well, now A minus, the anion, is going to be 2.83 moles, because 150 over 53 is 2.83, plus the 1 mole that I already had to start the problem, and that becomes 3.83. So that's our numerator. HA continues as it was before, 1. So I take the log of 3.83 divided by 1, and I end up getting 9.83. So we see a pH changes some, but not a lot. And that's all we're going to have time for in this one. This will be the last one for the first part of Module 8.